All right, so last but not least, we're going to talk about molar enthalpy of formation. And molar enthalpy of formation, by definition, is the energy change when 1 mole of a compound is made from its elements. And we're just going to say in their normal states. So, for example, oxygen in its normal state is not O, it's O2. And by definition, the delta H of formation, the molar enthalpy of formation for an element in its normal state, by definition, is 0. And that makes sense because to make O2 from its elements in its normal state would be making it from O2, so there should be no energy change. So if you look at your table and you see that some of these that are 0, it just means it's an element in its normal state already. So that's the molar enthalpy of formation, and it's not always positive, it's not always negative. It depends on what compound you're making and whether it is more stable or less stable than the elements that make it up. And so what I would like for us to do is maybe pick something on your reference sheet. We'll go ahead and write that molar enthalpy of formation equation and talk about what that means. So here are your heats of formation. There are more than this, you can Google them. But for these particular compounds, their delta H of formation values, and again, you got the little degree sign there for standard temperature and pressure. And then if it is an aqueous solution, then the standard conditions would be a 1 molar solution. And one thing that's important to look at is make sure that the state you are looking at is the state that you want. And one thing that gets mixed up an awful lot is water. And if you guys look at water down here, you have a different delta H of formation depending on whether or not you are making water in the liquid form or water in the gaseous form. So just pay attention to those kinds of things when you're using this table. So again, let's go ahead and use something interesting here. Let's use NaNO3, the solid, which has a delta H of formation of negative 467.9. And all the delta H being negative means is that NaNO3 as a solid is overall more stable than the 3 elements that make it up. And so what I'm going to do is start with Na. I'm only making 1 mole of that. So NaNO3 solid, and we said delta H is negative 467.9 kilojoules per mole. And so what we want to do is show how this is made up, 1 mole of this is made up from its elements. And so the standard state of sodium, the element, would just be Na, and it would be a solid. The standard state of nitrogen would be N2, and it's a gas. And the standard state of oxygen would be O2, and it would be a gas. Now, as far as standard states, if you don't know what the standard state of an element is, you can either Google it or you can look at a periodic table. Yours are not color-coded, I'm afraid, but a lot of periodic tables just show the solid, liquid, gas, natural state of elements, and so it's something you can just look up. Don't get too hyper about it. The problem with this is that it's not balanced, and so we are going to balance it as per normal, and then we're just going to adjust our ratio so that we have 1 mole of our compound. And so if I was going to balance this normally, I would do a 2 here. I would need 2 NAs. N would be fine, and then O, I would need a 3 here. And so this delta H is a per mole, so what I'm going to have to do is divide, now for my ratio, everything by 2, which means I wind up with, this is going to be 1 This is going to be 3/2, which is kind of crazy. This is going to be 1/2, and this is going to be just 1. And so here is a case where having fractional coefficients is actually acceptable and necessary if you're going to get just 1 mole of your compound sometimes. And then what you can do is, depending on how much sodium nitrate you are making, you can multiply that by the number of moles you're actually talking about. So if I have, a random 50 grams of sodium nitrate that I want to make, I could predict based on this how much energy would be released. So basically, if I were to draw a graph of this, what I would start with would be the elements Na, half of an N2, and 1.5 of an O2. And those in combination would be higher in energy than NaNO3. So going from those elements to the compound NaNO3, we're going to be releasing energy. But not every compound is like that. There are certain compounds where if you put them together, it's actually going to require energy, and that would indicate that the compound is less stable than the elements that make it up. So for example, I'm looking at, on your reference sheet, I'm looking for some positive values, and one that jumps out at me right away is in the middle-ish area, you have monatomic hydrogen, which is just H. And that's a positive 218 to form, kilojoules to form. And so instead of what we had last time, where the normal elemental state of hydrogen is H2, and I would need 1/2 of an H2, H would be way up here. And so it would require 218 kilojoules per mole to get from H2 to just monatomic hydrogen. And that should make sense because monatomic hydrogen should be a lot less stable than it would be as H2. And so it just kind of indicates to us how stable that compound is relative to the elements that make it up. But the important thing that you realize is that to write that thermochemical equation, you start with the elements in their standard states, and you are going to end with 1 mole of the compound. Delta H can be positive if it is less stable than the elements that make it up, or delta H can be negative if it is more stable than the elements that make it up. So you're going to do some work with that today as well. And with that, I bid you adieu and have a wonderful day and a fantastic weekend.